Welcome back to the class. In our previous lectures, we talked about unconstrained optimization problem. We also define the gradient methods and the Hessian in searching for the optimum. We know what is the necessary and conditions to reach the optimum, and we show you the iterative process of those two classic algorithms. Now let's look at the constraint version. Let us now show in the file, in our lecture file, where consider the continuous optimization problem of general nonlinear optimization problems where the minimization of f of x, we have only equality constraints. Let us consider only equality constraints, although in most cases we have inequalities. But here we have an assumption. All active inequalities are treated as equality. And the inactive inequalities become not as important. So we get rid of them. As a result, all relevant constraints become equality. Okay. So we have minimization of f and subjected to h. J number of h. We have j as an index. We have many nonlinear equality constraints. So any feasible point x must satisfy the constraints. Therefore, a small perturbation of partial x about the feasible point will result in a perturbation h partial h. Apparently, the point is only feasible if the perturbation h is 0. Okay. Because I'm at 0, and wherever I perturb or I move, I still want it to be 0. So we have the first order Taylor series expansion where the partial f is the gradient f partial x, denoted as the equation 2, and partial hj is gradient hj, denoted as this one. Okay. Therefore, we have n plus 1 nonlinear equations. And how many unknowns do we have? Well, we have n plus 1 unknowns. N plus 1 unknowns. So the final degrees of freedom is the number of unknowns multiplied by and minus the number of dimensions in the x minus the number of equality constraints. So that's the degrees of freedom. That's the final degrees of freedom. So let us separate the x into decision and state, state variable and a decision variable. Okay, state variable and a decision variable, where the decision variable is dimension m minus 1, because this is where the we say degrees of freedom comes from. Decision, make my decision. And how about state? State is the corresponding with respect to m, because state variable is the consequence of my decision. So when the decision variable perturbed, the perturbation in the state variable must conform to feasibility. That means I have two terms. One is state, one is decision. Decision is the degrees of freedom that I make. So when I make a move in the decision, the state has to be satisfy those constraint requirements, and which is h has to be 0, even in the perturbation version. So if we write the perturbation form, then we have equation 4. Equation 4 shows that this is the perturbation in the objective function and perturbation in the constraints. Okay. And then we can further separate into the state and decision. So this is separation into state and decision, because in previously we do I from 1 to m and n plus 1 to n. So this is related to decision. This is separate into state. Okay, so it's the same in the equality portion. So let's move to the next equation 5 is that's separate into state and decision. Okay, so here is the state and here is the decision. Again, what we're doing is, although we have design variable x, but because we have constraints, that means not all the x are free. Some of the degrees of freedoms in x are constrained by the equality. And we call those constrained by the equality is the state, because they are the consequence. And those are the free design variables, we call decision variables, are D. So here we have the objective function and equality. And this is equation 5 where we just reformulated the previous one with the variables that we defined, D and S. So we can also express equation 5 with the vector form. So this is the vector form. And the same as equation 5, right? It just looks a bit more concise. And if we take the equality constraint in the perturbation, if we take this one, so if we fix this one as the perturbation in S, then this has to be moved to the right. So as a result, it's in this format. That means the perturbation of the state can be calculated once you make a perturbation in the decision. So that's what we want. We want to know what are the consequences if I move from a point to another, still being able to satisfy all the constraint requirements. And if we take the entire values of S into the first equation of equation 6, then we have the whole thing. We have the whole thing. Okay. And then we say that, there's an equal sign, sorry, there's an equal sign. This is the bracket. Square bracket is a rearrangement of the, we rearrange the above into this one, okay. This is the perturbation of F. This is the perturbation of your decision. Remember, perturbation of your decision. In previous unconstrained problem, we have the perturbation of F, gradient F, perturbation of my design. Because I don't have constraints, so all the design variables are my free changing variables. Now, if we compare this to, this is the perturbation of F. This is the perturbation of my design or my decision. This is gradient. This is a rather complex form. This complex form is called a new constraint function. Because this is gradient F, if we call Z, this is a gradient Z. Right? This is called gradient Z. So if we call it gradient Z, that means gradient partial Z, partial D, because this is gradient F is partial F, partial X. We just use analogy. Partial Z, partial D equals the entire bracket term here. This is the, again, this is we call gradient of F, right? This is gradient of Z, but we don't have Z. Z is our new defined term. So this is, we call the reduced gradient of the function F. This is the reduced gradient. What is reduced? Reduced degrees of freedom. I don't have that much degrees of freedom, again, because of my equality constraints. Then I formulate a reduced gradient form where the reduced gradient is the original function perturbation with respect to the decision variable, with respect to state, the equality with respect to state and the equality with respect to the decision. This is called the reduced gradient. And the result is a feasible domain is in n minus m dimension. That's the dimension of D. So the function z is considered become unconstrained because we formulate a new unconstrained problem where all the equality constraints are embedded within this reduced gradients. So for any unconstrained problems, the necessary condition is partial f partial x is equal to 0. That's the necessary condition. And an analogy, we have fz d has to be 0. That's just an analogy, compare. Because I always compare an unconstrained problem and a constraint, equality constraint problem. Okay. All right, so that's the condition, necessary condition. So if we keep this form, then we know that this is, we call reduced gradient, and we have the necessary condition. Okay, so this is what we call reduced gradient, and it's for equality constraint nonlinear problems. If you have any questions, please let me know.